So far in this course, we've focused on the algebra of vectors and vector spaces. So how can we combine vectors using addition and scalar multiplication to get other vectors? And how can we transform vectors by applying linear transformations or equivalently by multiplying by matrices to get other vectors? And there's a whole other side to vectors, which is the geometry of vectors. Vectors have nice geometric properties that actually work pretty nicely with their algebraic properties. That is, there are relationships between them. And that's what this video is all about. I want to talk about vector geometry, and in particular, I want to talk about length of vectors and angle between two vectors. So let's start with length. So I'll start in R1, which might seem weird. We often don't use R1 as an example because it's too simple and you can't really see anything. But if I have a vector in R1, 2, has length 2. We can already see why we don't do a ton in R1, right? It seems boring, but we can just draw a quick picture here. What I'm saying here is, I don't know why I drew those arrows when I'm going to draw more arrows, is that R1 is just the number line, and if my vector is 2, I don't know why I drew that the same color, kind of not overlapping it. The length of that is 2. And then let's do one more example because it's not 100% trivial. This vector doesn't have length minus 3. Minus 3 can't be a length. It has length 3. Right, so I draw this out. I get length 3. Okay, let's move away from R1. As I said, kind of boring. You don't really see a lot there. Let's go look at R2. So due to limitations of Desmos or limitations of my use of Desmos, I can't draw arrows on the end, but let's imagine that this is representing the vector 2, 4, right? This has length, and I think everyone probably knows how to calculate its length, but regardless, we should do it. We want to find the length of the vector 2, 4. We use the Pythagorean theorem. And we say, well, the base of this triangle is 2. The height is 4. And the length of this is the square root of 20. So somewhere between 4 and 5. So that's length in R2. And we can also talk about length in R3. So let's look at this vector here. Now, what is this vector? This red vector is the vector 3 minus 2, 4. And if we kind of move around to this perspective, you can see that. Yeah, we have a negative y value, positive x and z. And the way you calculate this, if you haven't seen this in a while, you can actually derive it by drawing some lines. I'm not going to do that, but you kind of have this extended version of the Pythagorean theorem where you square each entry, add them all up, and take the square root. And so we end up getting the square root of 29. So a number between 5 and 6. Didn't quite fit these onto the same screen. Okay. So that's length in R1, R2, and R3. And it is probably not surprising. I wouldn't be making this video if it were just about R1, R2, and R3. We can talk about length in higher dimensions. So and first of all, why would we want to do that? So why would we want to talk about the length of a vector in higher dimensions? Well, the reason we do anything is because it's useful. 2 examples of why thinking of length in higher dimension are useful is we want to be able to talk about the distance between things in higher dimension. When we're doing things like least squares regression, which we're going to do in the future, we need to understand what it means for 2 points in higher dimensions to be close or far from each other. And for that, we need a notion of distance, and we get distance from having a notion of length. We'll want to know what the closest point to something is. The other reason is that it actually makes sense in higher dimensions. And one way of thinking about this is that when I'm looking at the length of this vector in R3, I'm thinking of this as a vector that lives in a one-dimensional subspace, right? It lives in its own span. And so it lives inside this line. And so even though it is existing in a bigger dimension, length is really a one-dimensional thing. And so I should be able to talk about its length. And so when we get up to higher dimensions, that's how we're thinking about it. We'll say, look, this vector is in R7, right? It's 7-dimensional, but if we only consider the span of this vector, it's in a one-dimensional space. We should be able to talk about its length. And so how are we going to do that? Well, we're not just going to make something up. As it turns out, there's a bunch of properties that we want length to have, and we want our notions of length in higher dimensions to match up with our notions of length in lower dimensions. And it turns out for this to happen, there's only one way we can define length, and it's what you might guess. So let's start with R4, right? And so here we have this pattern here, right? The length of this vector, we squared the coordinates, added them up, and took the square root. Same here, we squared, added up, and took the square root. And one of the reasons I did R1 length is we can get the same thing, right? If we square 2 and then take the square root, we get 2. If we square -3, we get 9. We take the square root, we get 3 back. So we see this pattern, and it turns out that, for instance, the length of a vector in R4, to figure that out, we'll take the square root of each of its coordinates squared, add it together. In this case, we would get the square root of 14. And we're not doing this just because we see a pattern. This is the only reasonable way to do it, to get the properties of length that we would want to have and to match up with lower dimensions. And in general, the length of, if we have a vector v1, v2, all the way up to vn, this is living in Rn, we square each coordinate, we add them all up, right, the dot, 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 indicating all those middle terms that I didn't want to write down, and we take the square root. Okay, so that's length in Rn. I want to take a brief, unmotivated divergence into what's known as the dot product, and I'll come back and motivate it. But I think you need to see it first before it can be motivated. If we have two vectors that are in the same space, so they have to both be the same dimension, then we define the dot product v dot w to be the thing we obtain by multiplying their coordinates and adding them together. And we're multiplying corresponding coordinates. So for example, if I take 3 minus 1, 2, take the dot product with 7, 5, 6, I take 3 times 7 plus -1 times 5 plus 2 times 6, and I get 21 minus 5 is 16 plus 12 is 28. So that's the dot product. Hopefully one example gives you a sense for what it is. Okay, totally unmotivated, right? I'm not just defining things for no reason though. Initial motivation of the dot product, that's not that compelling. When you look at this formula, you can convince yourself that this interior part, this formula for length, the thing under the square root is this vector dotted with itself. So we've used the dot product already, and I should introduce some notation. I don't always want to have to write the length of this. And so I'm going to write this as double bars on either side of V, indicating the length of V. Okay, so we have this formula for length. This new mysterious thing called dot product shows up in it. Not motivation for using the dot product yet. It's one of those things, though. It's going to show up everywhere as we start doing vector geometry. And once that starts to happen, it's worth defining it. But we need to define it before we can use it. Okay, so that's length. And I don't think length is too bad in the sense that the formula for length is somewhat intuitive. If I asked you to guess what the length of this vector would be, if you had seen length in R2 and R3, I think this is what you would guess. And I generally find people don't really object to this. Talking about angle in higher dimensions, I think starts to feel a bit weirder, but it does ultimately have the same properties where you get a formula that looks in some sense the same as the formula for R2 and R3. But to do this, we should discuss what happens in R2 and R3. So we can't even talk about R1 because angle in R1 is not interesting. Angle is a two-dimensional thing. So let's go back to R2. So what view do I want here? So let's talk about angle in R2. Scroll down where we have some space. And to talk about angle, I need another vector. And again, I'm thinking of these vectors as both starting at the origin, right? So I have this green and this blue vector. And so I'm trying to find the angle between these two vectors. And the green one, which is on the left, angle is symmetric, right? It doesn't matter the order I write them, but is -1, 3, and this blue vector, which is 2, 4. How am I going to find this thing? How am I going to figure out what it is? It's a defined thing. And I guess, first of all, I should point out, when we have two vectors, you can see in this picture, we could talk about two different angles. And one of them is always going to be less than or equal to 180 degrees, or pi radians. And one of them is going to be bigger. We're always talking about the smaller angle, right? So this is this kind of top angle here. And in this example, we'll see this. You actually could find this angle using basic geometry, but that's not always the case. In general, how do we find the angle between two vectors? Well, the idea is that I can draw in this third line, and this is a vector now not based at the origin, and I create this triangle, and you can convince yourself that you know everything about this triangle, right? We know the length, in particular, the lengths of all three sides, right? We can figure them out using the Pythagorean theorem. And so we should be able to figure out the size of this angle between the green and the blue vector. And the way we do this is what's known as the law of cosines. So the law of cosines you may or may not remember having seen this. I guarantee you've seen it at some point in your life, even if you don't remember it. It says that, look, if we have a triangle and we know the length of 3 of the sides, and we want to know the angle theta between 2 of the sides, the way we find it is that the cosine of that angle is this is incidentally, I mean, if you have the law of cosines memorized, props to you. I teach math and I don't have the law of cosines memorized. It's given by this formula: a squared plus b squared minus c squared over 2ab. That's the cosine of this angle, and then you take the arc cosine to get the angle. Okay, so in this example, we could work this out if we wanted to, but I don't really want to go through the kind of detailed geometry because it turns out that we can rewrite this in terms of vectors. And I'm not going to go through the algebra. It is just algebra. You can figure out in R2, write down the vectors in terms of their coordinates, figure out what the length of the green vector is, what the length of the blue vector is, what the length of the orange vector is, and you could solve for theta. But in terms of vectors, what the law of cosines tells us, and let's flip away from the picture so that we have a little more space, is that if we have a vector v and a vector w, and we want to know the angle between them, theta, let's clean this up a little. That the cosine of theta is given by v dot w divided by the length of v times the length of w. And these two statements are equivalent. That is, you can derive this formula from this formula by thinking of these things as vectors, or you can derive this formula from this formula by drawing in a third line and thinking of these things as triangles. It's just algebra. It's complicated algebra, complicated enough that I don't want to put it on the video. But what I want to do is I want to go in and figure out the angle for our example. So in our example, v was the vector -1, 3, and w was the vector 2, 4. And what we get here is that the cosine of the angle between them is v dot w. Actually, incidentally, this is a good place. Pause the video, try to solve this yourself, and then check what you got. When we dot these two vectors, we get 10 divided by the length of v is the square root of 10, the length of w is the square root of 20, and we actually get 1 over the square root of 2, and you may recognize this. The arc cosine of this, or the inverse cosine of this, is pi over 4, or 45 degrees. This may just be me, but personally, so the first statement is inherently true. Radians is useful for calculation. But for me, visually, degrees makes more sense, right? If you tell me that an angle is 2 radians, I have no idea what that is. But if you tell me that an angle is 160 degrees, I quickly have a picture in my head. I don't think 2 radians is 160 degrees. I was just using that as an example. So I like to state them both ways, radians and degrees. So this is the angle between our two vectors. Let's go back to our picture and convince ourselves, especially with this line drawn in. One, looking at the geometry, but you can convince yourself that the green and the orange lines create a 90-degree angle, which leaves 90 degrees left, but also that we have an isosceles triangle here. And so each of the two remaining angles are 45 degrees. So geometrically, we can actually see this works, right? This is a 45-degree angle, but we didn't need the geometry. And in fact, and this is important, we didn't need the picture. We calculated the angle between these vectors. We didn't use this picture. It's there, but we just applied a formula, which is good because as we move to higher dimensions, we won't be able to visualize exactly what's going on. Okay, so we have this nice formula using the law of cosines to figure out the angle between two vectors in R2. What about R3? And I think the R3 picture is really important. I think that understanding angle in R3, so if we want to know the angle between this red and this blue vector, really gives you the sense for how angle is working in higher dimensions. What does the angle between two vectors in R3 even mean? Because angle is a two-dimensional thing. How do we figure out what the angle is? Well, given two vectors that aren't on the same line, they lie in a unique plane. Here, I've drawn this in orange. Right, so these two vectors, they live in R3, but if I want to know the angle between them, I want to know how they interact with each other, I can just look at their span. That forms a plane, a two-dimensional thing, because I only have two vectors, And in 2 dimensions, angle makes sense. We just figured out how to deal with angle in 2 dimensions. And so given that these live in a 2-dimensional space, it makes sense to talk about the angle between them. Now, how do I find the angle between these 2 vectors? And so let's say what these vectors are. So I want to know the angle between the red vector, which is 3 minus 2, 4, and the blue vector, which is minus 6, 1, minus 1. How do I figure that out? Well, it turns out that that law of cosines formula that I wrote down earlier works in 3 dimensions as well when we're thinking of things as vectors. And as we move up in dimensions, this is harder to show, but it does work. You can work it all out if you want to do the algebra. So what is this angle? It's going to be given by cosine of the angle is going to be v dot w divided by the length of v times the length of w, somewhat miraculously, it seems. And so let's work this out. Let's move away from the picture. So try this on your own. Try to figure out what this angle is. And you hopefully will get the same thing as me. We get negative 24 divided by the square root of 29 times the square root of 38. And when we take the inverse cosine of this, we get 2.379, I'll write radians. Radians are technically unitless, but just to be clear, which is the same as 136.3 degrees. And again, the nice thing about degrees versus radians is when I go back to this picture, so yeah, 136 degrees, that's about right. But 2.37 radians, I don't know what that is, right? Harder to visualize. So this is believable. Okay, so before generalizing angle even further, I want to look at one last thing, which is perpendicular vectors. So let's go to this example, and let's get rid of these 2 lines, but let's add in a red vector. These 2 vectors are perpendicular. And what you'll notice, if you try to calculate the angle between them, when you do this, you'll get, if v is the blue, well, it doesn't really matter, v dot w, whichever order you multiply or you do it in, you're getting 2 times 2 plus 4 times negative 1, you get 0. I wrote angle equals, that's not true. The cosine of the angle equals that. You get 0, and the arc cosine of 0 is 90 degrees, or pi over 2. So theta is pi over 2, 90 degrees. And what you realize is it doesn't matter what the lengths of the vectors are. The only way for this quantity to be 0 is for the top to be 0. So vectors will be perpendicular if their dot product is 0. And that's going to work as well in 3 dimensions, because the same formula applies. Vectors will be perpendicular when their dot product is 0. All right, so how do we take angle into higher dimensions? You should already be able to guess that the answer is going to be this formula. Because 2 reasons. One, the pattern's there, right? But also because this formula is somewhat dimensionless, right? It's not dependent on on what n is. And as it turns out, similar to length, one, we can define angle in higher dimensions, and the picture you want to look at is this one, right? In higher dimensions, here we're just in R3, but even if we're in R4, if we're talking about two vectors, their span is a two-dimensional subspace of R4. And in two dimensions, it makes sense to talk about angle, and so we can talk about angle between two vectors. They live in a two-dimensional subspace. And so when we get into higher dimensions, we can't really visualize this directly, but it turns out that if we want angle to work the way it should, if we want it to work out and have the same properties as angle and to line up with what goes on in lower dimensions, the angle between two vectors is given by this formula. That the cosine of theta is v dot w divided by the length of v times the length of w. And this will be useful. Angle will be useful for us in higher dimensions. In particular, we'll be interested in when two vectors have a 90-degree or pi over 2 angle between them. What we would call perpendicular, but what we'll start calling orthogonal, and generalizing the idea of perpendicular vectors in regular 2- and 3-dimensional space. And so just real quickly, we can do this in, for instance, R4. So we have no visualization of this, but if, for instance, I want to know the angle between 1 minus 1, 0, 2 and 3 minus 2, 1, 0, I'll call this V, I'll call this W. The angle is going to be the arc cosine of V dot W divided by length of V, length of W. In this case, the dot product of these two vectors is 5. The length of the first is the square root of 6. The length of the second is the square root of 14. And this angle ends up being 0.994 radians, or about 56.9 degrees. So even though we can't visualize these vectors, we can't see where they do live in a two-dimensional subspace. And in that subspace, this is the right notion of length, or sorry, of angle. Okay, so I know this is a long video, but hopefully this has been useful, mainly in understanding what length and angle are, right? I could just give you these formulas, but hopefully it's helping you understand kind of how they work. I want to mention a few important properties / uses of these things. So let's start with the uses, like specific cases. One of the main uses of length is the notion of the distance between vectors. And let's understand this with a picture. That back to two dimensions, if I want to know the distance between these two vectors that I was considering before, remember we think of vectors sometimes as arrows, but sometimes it's just points. The distance should be the length of this orange line. And the length of this orange line, well, this orange line, if you think back, represents the difference between these two vectors, right? So in either order, I could do this either way. If I subtract the two vectors, I get the vector 3, 1, which is what this orange line represents if we think of it as moving up and to the right. So the distance between these vectors should be the length of this, which is the square root of 10. And so, in general, what should the distance between two vectors be? It should be the length of their difference. because their difference is representing that line that would connect the points, right? And the distance between them is the length of that line. So this is one important application of length, right? It allows us to talk about the distance between two vectors. I want to give an important application of angle, which I already hinted on, but let's just look at writing here. So I want to talk about the notion of orthogonal vectors. Orthogonal really is the same thing as perpendicular when we're talking about R2 and R3, and probably when we're talking about Rn, depending on who you talk to. Orthogonal is really just a fancy word for perpendicular that applies in more general contexts. There are different ways to take things like dot products, and we want some notion of orthogonality. But two vectors are orthogonal if their dot product is 0. Now, as we saw before, this means that either the angle between them is pi over 2, which is 90 degrees. So this is this notion of perpendicular. Or there's one other way to get the dot product to be 0. If one or both of the vectors are just the 0 vector, right? If you have a vector of all zeros and you take the dot product with another vector, you're going to get 0. But you can't necessarily talk about the angle between those vectors. Okay, so orthogonality and kind of this similar notion of perpendicular vectors is going to be important to us, and that's going to be our main application of angle. So these are going to be kind of the two main applications of length and angle that we use: distance between vectors and deciding whether vectors are orthogonal to each other. There are a few properties I wanted to mention of length. And I guess they also involve angle as well. The first one is that the Pythagorean theorem works in higher dimensions. If two vectors are orthogonal, so if the vector or if their dot product is 0, then when we add them together, square it, that's the same as separately squaring the lengths of the vectors and adding those numbers together. Basically, we're saying if we have a right triangle, we can find the length of the hypotenuse by squaring the lengths of the two legs, adding them, and taking the square root. The Pythagorean theorem still applies in higher dimensions, and I'm not going to draw a picture because it's in higher dimensions, right? And this makes sense, though, right? In that anytime we're talking about two vectors, they live in a two-dimensional subspace. And so it makes sense to talk about whether the Pythagorean theorem applies. I just can't draw it in full generality. And there's another property of length that you might take for granted, but is really important. It's called the triangle inequality. And the triangle inequality basically says that the shortest distance between 2 points is a straight line. Or in other words, that one leg of a triangle has to be at most as long as the sum of the other two legs. And this is for any vectors v and w, right? The if v dot w is 0 is just part of the Pythagorean theorem. So this is one side of a triangle, and these are the other two sides of a triangle. We're saying that walking along two sides of a triangle is at least as long as just walking in a straight line between 2 points. Okay, so at this point, I've covered everything I wanted to about length and angle. I wanted to say one last thing, and you can skip this, I guess, if you want. It's not something that will directly apply to anything, but I wanted to give some insight as to why the dot product is connected to length, or sorry, to the angle between two vectors. So going all the way back up to when we were talking about the dot product, what is the dot product of two vectors actually measuring? Well, we're multiplying the pairs of coordinates together, right? So here we multiplied 3 times 7, -1 times 5, 2 times 6. And what you notice is that if the two coordinates have the same sign, so 3 and 7 are both positive, you get positive 21. You get a positive input to the dot product. Also, if they were both negative, right, those would cancel, you would get positive. But then when your two coordinates have different signs, like -1 and 5, you get a negative input into the dot product. And so in some sense, the dot product is measuring to what extent are vectors pointed in the same direction in a coordinate by coordinate way, and taking into account the magnitude, right? Saying, look, these are pointed kind of in the same direction in the first coordinate, and these numbers are big. They're pointed kind of in the same direction in the third coordinate, and these numbers are small. And they're pointed in different directions in the second coordinate, but these numbers are even smaller. And so then your overall dot product, here you get a positive number, and this is saying that the coordinates tend to be pointed in the same direction. Now, if you get a negative dot product, here when we took this dot product, we got -24. We're saying, look, the coordinates tend to be in opposite directions, right? In fact, all of them are in opposite directions here. But a negative means they tend to be pointed in opposite directions. And that's saying these vectors are kind of going in opposite ways. And notice this corresponds to here these, if we look at like this dot product, we get a positive dot product. They tend to be pointed in the same direction. The angle between them is less than 90. Here, these vectors tend to be pointed in opposite directions, coordinate by coordinate, and we get an angle that's bigger than 90. And then finally, if we have vectors that have a dot product of 0, we're saying, some of the coordinates are pointed the same way, some are pointed opposite ways, but overall they're kind of just going totally different directions. Not the same way, not opposite each other, just kind of off at different angles, which is when they're orthogonal. They have a 90-degree angle between them. And so when you think of it this way, I think it kind of starts to make sense, one, why the dot product could be useful, right? It's kind of just going through coordinate by coordinate and asking whether things are pointed in the same direction, and also keeping track of how much they're pointed in that way. And in particular, that this should have something to do with the angle between the vectors. All right, so I know this was a long video, especially for one of these conceptual videos, but if you stayed till the end, thank you, and hopefully that was useful.